Hello, everyone. Welcome back to my video tutorial for microbiome data analysis. In my previous video tutorial, we built the OTU table. So let's have a look at the data structure for the example data. Global patterns again. You can see we built the OTU table. Next one will be the text table. So today we are going to build the text table, sample data, phylogenetic tree. Then we can use the data to create a phyloseq object. So first we can prepare the text table. To prepare the text table, we need a training set of classified sequence. This is the advantage we are analyzing the 16 sRNA sequence because there are lots of training data set available for analysis. So we are going to use the RDP training set. For today's demonstration, you can use this link to download the data set. If you have a look at this link, there are lots of other data sets available for you to use. So let's load the data as a reference data set. Then we can assign the taxonomy by comparing the sequencing variance in the data to the RDP train set. So we can use the assign taxonomy function to build the text table. Let's run the code to build the text table. We can run. Okay, you can see we built the text table for the sequence in the OTU table. So after the text table, we need to prepare the sample data. You can download the sample information CSV data from this link. Because it is a CSV file, we can use read CSV function to load the data in as a sample data frame. Let's load the sample data. We can click the sample data frame and have a look at the sample data. You can see we have the sample ID. In total, we have 672 samples here. I showed you when we prepare the OTU table. We have the forward sequencing R1 and the reverse sequencing R2 data for the same sample. So in total, we have 672 sample information here, and there are 46 columns. You can see the sample ID is different from our OTU table. Let's have a look at the OTU table. You can see the row names are F3D0, but in the sample ID, it looks different. So we need to make some changes to make sure the row names are the same for the sample data and the OTU table. So first we can change the sample ID name. You can see we can use the paste and the gsub function to change the sample data name. Let's run. So we created the sample ID column in the sample data. Let's have a look at the sample data again. You can see now we have the sample ID column in the last column. The sample ID name looks the same as the OTU table row names, but you can see here we have a repeat name for each sample because we have the same sample for forward and reverse sequencing. So next we need to get rid of the duplicated sample name. Let's remove the duplicate sample name. We can run. If we have a look at the sample data now, you can see we only have 379 entries. So we remove the duplicate sample names. Let's have a look at the sample ID again. Now you can see we only have one sample name for the sequencing. So we kept the forward sequencing information because you can see here all the samples are R1. So next we need to make one sample ID change. Because the sample ID is different for the number 124 and we change it to the 125. So this is the problem for sample data preparation. If you are going to analyze your own data, you should know the sample information very well. So let's run the code to change the name. Now we can have a look to see if all the row names in the OTU table is in the sample data ID. Let's run. You can see it is true. So now all the sample names in the OTU table are in the sample ID. So let's have a look at the sample data again. You can see that at the moment the row names was arranged by the number. It is not the sample ID name, so we can set the sample ID name as the row names for the sample data. If you have a look now, you can see the row names are the sample ID name. You can see here we have 379 entries, but in the OTU table, we only have 360 entries. So we need to subset the data. First, we just want to keep the columns. There are 14 columns we want to keep from the sample data. If you remember, we have 47 columns in the sample data. So let's select the column names that we want to keep for our analysis. So next we can subset the sample data by the row names from the OTU table. Here we only have 360 IDs. Then just keep the 14 columns we selected here to subset the sample data. Let's run. So we prepare the sample data now. Let's have a look at the global patterns example data again. You can see we have the OTU table, we have the text table. We prepared the sample data just now. So the last data we need is the phylogenetic tree. So in next step, we are going to construct the phylogenetic tree. Because the DA2 sequence interference method is reference-free, I showed you in the beginning. So we need to construct the phylogenetic tree in order to relate the inferred sequence variants in this dataset. So first we need to align the sequence in the OTU table. To do so, we need the decipher package. So we can load the decipher package. Then we can get the sequence information from the OTU table. Then we use the sequence as the names. Now we can align the sequence. Let's run the align sequence function from the decipher package. You can see it is running. After it finishes, we can have a look at the analysis. So let's go have a look at the alignment. First, you can see it determined the distance matrix based on the shared items from the sequencing data. Then it clustered the sequence into groups by sequence similarity. After that, it aligned the sequence again. Then determine the distance matrix based on the alignment. Then recast the sequence into groups by similarity again. So after that, it realign the sequence again, determine the distance matrix based on the alignment, and then finally recast into groups by similarity and realign the sequence again. So that's the step to align the sequence. In next step, we can construct a phylogenetic tree. Use the Finalizing R package. We can load the package first. Then we can use the alignment information to construct a neighborhood joint tree. Let's run the function to construct a neighbor joined tree. So after that, we can fit a GTR maximum likelihood tree for the analysis. So we can run the code down here to fit the likelihood tree. It will take a while to fit a GTR maximum likelihood tree. Okay, you can see we finished the analysis. We have the fit GTR data here. We can click the data and have a look. You can see in the fit GTR, we have a tree in the tree data slot. So we can use this tree to build the phyloseq object. So now we have the OTU table, we have the text table, and we prepare the sample data. Then we have the genetic tree information built in the fit GTR data. So now we can use all the data to create a phyloseq object. So we can use the phyloseq function to create the object. Let's run. You can see it is very quick. We created the phyloseq object. It is here. It only has 1.2 megabyte. Let's click the object and have a look. You can see now in the phyloseq object, for our analysis, we have the OTU table, we have the text table, we have the sample data information. We also constructed a phylogenetic tree. So the reference seq data slot is empty because we used that reference sequence to build the text table. We don't need the reference seq information anymore. For the rest, microbiome data analysis using the phyloseq package. So now we can save the data. We will save it as the phyloseq object. Let's save it. Then, in my second part, we are going to perform microbiome data analysis using the phyloseq package. Then we can load this saved data back to R to do the rest demonstration. So I'm going to stop from here for today's video tutorial. I hope to see you again in my second part of video tutorial.